Good evening, students. This lesson is the second lesson in the Magnetism and Electricity module, and it's going to be covering the electric potential energy. And we will also be doing a practice problem at the end of this presentation as well. Electric energy. The motion of charged particles carries energy. So if we look at the work done by moving charge in an electric field, we find that the equation, the change of potential energy, equals the negative work. Expanding the definition, we can get the change of potential energy equals the force times the distance, because remember that work equals the force times the distance. Electrons move because of the electric field, but remember the direction of the force of the electron is opposite the direction of the electric field. By moving the equation for the electric field, we can get that the force of a charge in an electric field is E equals F divided by Q, or if rewritten the equation, F equals E times Q. So we plug in what we get, the equation for the energy stored in a charged particle in a uniform electric field, we can obtain the formula, the change of PE equals the negative QED. And we'll talk about what all of these mean in the practice problem as well. The value depends on how the strength of the field and the value of the charge and how far it is moved in the field. We store electric energy by pumping electrons in the direction of the field. So when the circuit is connected, the electrons flow opposite to the file and release that energy. Here is a picture of a uniform electric field. The potential energy of a positive charge increases as it moves opposite the field. For a negative charge, it increases as it moves in the direction of the field. The two charges run parallel, and then there is a constant field running between the two plates. So what I just described is the picture that you see in the slide with the positives on one side and the negatives on the other. And just like the electric field is a ratio of force to charge, the electric potential is the ratio from energy to charge. Usually when discussing the parts of a circuit, we use the value for the electric potential difference. The electric potential difference, often just called the potential difference, is electric potential energy per unit charge. The equation V equals PE divided by Q can be used. So here's a way to calculate that potential energy. The electric potential difference, like I said, is usually called the potential difference, is a ratio of the charge and the potential energy between 2 points per unit charge. So that equation can be expanded as the change of V equals the change of PE divided by Q, also equals the negative E times D, distance. Potential difference, the unit for potential difference is volt, also known as voltage, and can be represented by a V. 1 volt is a difference of 1 joule per coulomb of charge. So that is another way of saying the statement is 1V equals 1J, 1 joule divided by 1 coulomb of charge, 1C. The larger the potential difference, the more energy per unit of charge, and then the amount of current that flows through a circuit is what can be harmful to living things. It's not the voltage. So that is a common misconception of students. Also, please just star that relationship to make sure you saw that relationship in your virtual lab for this unit. Again, it's the larger the potential difference, the more energy per unit of charge. All right, so now we are going to go through that practice problem for this section of the module. It states 2 charged objects are placed 0.045 meters apart. The one on the left has gained 3.75 times 10 to the 13 electrons on it. The one on the right has lost 6.28 times 10 to the 13 electrons. The first question states, what is the charge on the left of the object? So all we have to do is plug in our formula here. The 2 charges, again it's 3.75 times 10 to the 13th, which is given to us in the problem, times the one times the constant that we talked about in our first lesson, negative 1.602 times 10 to the negative 19th, and we should get negative 6.10 times 10 to the negative 6. Same thing, what is the charge on the right object? Again, we plug into our formula. Again, if you haven't watched the first lesson video, make sure you know that constant value. We covered it. So we're going to now do the right one, which is given to us in the problem, 6.28 times 10 to the 13 times the constant 1.602 times 10 to the negative 19th. And we should get 1.01 times 10 to the negative 5th coulombs. Letter C says a third charge is placed halfway between the two charges. What is the magnitude and direction of the electric field at that point? So first of all, you have to remember that electric fields are vectors. So the negative 1 on the left points toward it, and the positive charge on the right points away. So both point left is what we're trying to get at here. Halfway between 0.052, which is given to us in the problem, so that means we're going to divide it by 2. That just means half. So it's going to be 0.0225 away from each other. So on the left side, we're going to plug in this equation, what we have here, which is 9 times 10 to the 9th, which is also that constant here with the k. We covered that in the first lesson as well. Times the constant what we calculated in letter A up here, 6.01 times 10 to the negative 6. Divide that by the distance, and then don't forget to square it before you divide, and you should get 1.07 times 10 to the 8th. For the right side, same constant from that lesson 1 times what we calculated in part B, divided by that distance squared, and we should get 1.80 times 10 to the 8th. So they're going to point in the same direction because of what we talked about in this part. So we're going to add the two values. So after we add these two values together, we should get 2.87 times 10 to the 8th. And don't forget that it's a vector, so you must have the direction, so it's going to be left. Letter D says, what is the magnitude and direction of the force if the charge has a value of negative 5.18 times 10 to the negative 4th? So here we have the equation that we talked about in this lesson. We plug in what we just calculated, 2.87 times 10 to the 8th, times the charge here, 5.18 times 10 to the negative 4th, and we should get 149,000 to the right. Again, this is opposite to the field because it has a negative charge, which is given to us in the problem here. Letter E says, the same test charge is moved to a place where that it is uniform electric field equal to the answer in C. The test charge is moved 3.50 millimeters in the direction of the field. What is the change in energy of the charge? So the first thing is you have to convert the distance here. So that is what this step is showing you, 3.50 millimeters, converting into meters, so we should get 0.0035 meters. A lot of students forget this step, so maybe that's where you're making a mistake, so double check that. And then we're going to plug into the formula for the potential energy. Negative 5.18 times 10 to the negative 4th times 2.87 times 10 to the 8th times the distance 0.0035, and what we should get is 520 joules. Letter F states, what is the electric potential difference between the starting and ending point of the charge as it moves? So we now are going to use this formula, plug in what we know, so that's negative, because of the direction, 2.87 times 10 to the 8th times the distance, 0.0035, and we should get 1.00 times 10 to the 6 volts. Thank you for watching, and please let me know if you have any questions.